All right, so welcome to the Kepler's law and gravity questions. We're going to start with number one. So number one states, which graph best shows the general relationship, right? Relationship question between a planet's distance from the sun, that's one category, and the sun's gravitational attraction to the planet. So we know, right? As a planet's distance from the sun, what is happening to the sun's gravitational attraction to the planet? When you're looking at a graph and you're looking at the, the x-axis, one of the things to keep in mind is that the category for the x-axis is always going to be increasing. It is always going to be increasing. So that means that we have to ask ourselves this question. As the planet's distance from the sun is increasing, what is happening to the gravitational force? What is happening to the gravitational force? So in our notes, right, we've learned, let me take a look. We've learned that the more distance between two objects are, the weaker the gravitational attraction, right? So if the distance between two objects are getting further apart from each other, that means that the gravitational attraction is going to be weaker as you go away, as you're going farther apart between the two objects. So when we look back at our question, we know that our gravitational pull attraction, our gravitational attraction force is going to be weaker. We know that it's going to be weaker as the distance increase. So which graph shows me that as you get further away from the sun, that the gravitational force is going to decrease? And the one that shows that is choice 4. All right. So as the planet's distance from the sun gets farther and farther, right, the sun's gravitational attraction is going to get weaker and weaker. And so number 1 is 4. All right. So number 2. Number 2 says the symbols below represent star masses and distances. So the small circle represents a star with a mass the same as the sun. The larger circle represents a star with a mass greater than the sun. D represents a certain distance between stars. 2D represents twice the distance between star center. Which diagram shows two stars that have the greatest gravitational force between them? So when we look at our notes from yesterday, one of the things that we keep in mind is that there are two factors that affect the gravitational force: mass and distance. Mass and distance. If we take a look, right, from our notes, if you have between the two objects, whichever scenario contains the greater masses is going to have the stronger gravitational attraction, right, as we see here. So you have two objects with the scenario that has more mass, more gravity, right? More mass, more gravitational attraction. And then the closer you are, if we take a look, the closer the objects are, the more gravitational attraction force is between them. So when we're looking back at our example, one things we got to see is the fact that we're looking for two stars for the greatest gravitational force. We need them to have large masses. We need the best scenario with the largest masses, right? And we need the scenario with the closest distance to get the greatest gravitational force. So which scenario contains the largest masses and which scenario contains the closest distance? And that is going to be choice 3. Choice 3 has the largest masses between them, right? And they have the closest distance between them. All right. That's so number 2 is choice 3. All right, number 3. It says if the average distance between Earth and the sun were doubled, what changes would occur in the sun's gravitational pull on Earth in Earth's period of revolution? So they're saying, imagine this, all right, this is the sun and this is the Earth, right? And so they're saying this is, let's say this drawing is the representation of the distance between Earth and the sun. They're saying in this new scenario, what if the distance between the Earth and the sun were doubled? All right. And so therefore, now they're saying what will happen to the gravitational pull on Earth and what would happen to the Earth's period of revolution. So let's go with the gravitational pull on Earth, right? If you're going farther away from the sun, so if your distance increases, further, what happens to the gravitational pull? Well, we learned in class that the farther objects are away from each other, the weaker the gravitational pull is. The weaker gravitational pull is. All right? The farther that you go. And so, therefore, we know that the gravitational pull will definitely have to decrease. So that crosses out 3 and 4 because it's saying that the gravitational pull would increase, and that is incorrect. So we know the gravitational pull would decrease. All right, that's the first thing. The next thing, if I go ahead and erase now, let me erase. There we go. All right. Now, as you get further from the sun, what happens to your period of revolution? Well, according to Kepler's third law, to summarize, let me just clear this up. Kepler's third law says that the farther from the sun a planet is, the longer it takes to revolve around the sun. Therefore, it has a longer period of revolution. So that lets me know that if Earth's distance got farther, all right, if Earth's distance got farther, then that means that it'll take a longer time to go around the sun, right? If this is the sun, right, this is the Earth, let's say this is the original pathway, right? I know my drawing is horrible. Now, in the new scenario, and let's do it green, and let's say the distance from the Earth is now double, right? So this is the new scenario of Earth, right? You'll see that in the new scenario, the Earth has a longer pathway to travel. And so because the Earth has a longer pathway to travel, the period of revolution will increase. The period of revolution will increase. All right? And that's why the correct answer is choice 1. Even if you take a look at the reference tables, right? And I'll just clear this up. Look what happens as you get further from the sun, right? If you start with Mercury, you start at 57.9 million kilometers. It only takes you 88 days to go around the sun. Now, when we look at Neptune, where the distance is 4,498.3 million kilometers, it went from 88 days to 164 years. So the farther you are from the sun, the longer it's going to take for you to go around the sun. All right? And so that's why, once again, the answer, the answer is, sorry, I just made a mistake. The answer is choice 1. All right, the answer is choice 1. Oops, right here. All right, so for number 4, one factor responsible for the strength of gravitational attraction between a planet and the sun is blank. So if we take a look at our notes, all right, if we take a look at our notes, oops, sorry, as we take a look. So there are 2 factors that affect the gravitational force, right? This category right here. There are 2 factors that affect the gravitational force. The mass, right? The mass of the objects and the distance between the objects. So we're going to choose an option that either talks about the mass between the objects or the distance between the objects. And when we take a look, the option that either talks about the mass of a planet or the sun or the distance between the planet and the sun is choice 2. All right. Right. So either the distance between the planet and the sun or the mass of the planet and the sun, those are the only 2 things that affect the strength of gravitational attraction. So the correct answer is choice 2. All right, number 5. Number 5 says, in which type of model are the sun, other stars, and the moon in orbit around the Earth? So what model is the sun, other stars, and the moon in orbit around the Earth? Okay. So that lets me know, if I was to draw it out, right, this is the Earth. So therefore, that lets me know they're talking about where the sun is orbiting around the Earth. Other stars, right? I'll just, S for star, that's orbiting the Earth. And even the moon, I'll just write an M for moon, right? That is orbiting the Earth. And when we take a look, right, when the Earth is in the center, that is only one type of model. When the Earth is in the center and all other objects are orbiting the Earth, that is known as a geocentric model, right? Because it's an Earth-centered model. All right? If the question said where the sun is in the center, then we would say heliocentric. But because it is the Earth that is in the center and all the other objects are orbiting around the Earth, that lets me know it has to be a geocentric model.